Hi, and welcome back to my Physics Online video lecture series. Today's lecture we're going to be talking a bit about electric field lines and drawing electric field lines. So this technique is something that was developed originally by Michael Faraday, and it's a nice technique for kind of visualizing what the electric field sort of looks like or is doing through a given region of space. It's also a nice, powerful tool for helping us to solve for electric fields, at least conceptually, or setting up the problem to solve for them via a technique called Gauss's law, which we'll learn about in a different video. So there's basically a set of rules for drawing these field lines and also for what they do. So again, the electric field lines idea was developed by Michael Faraday, who we will, of course, encounter again in this course. The basic idea is that these lines can show basically the magnitude and direction of the electric fields in a region of space. So it shows both magnitude and direction, at least as a representation. And by the way, this technique works for stuff other than electric fields. You can do it for gravity fields and magnetic fields as well. But we're going to learn it for electric fields here. And it is a representative drawing. So that basically means that, as with any representative drawing, some features or details may be left out. It's kind of like looking at a map as opposed to actually visiting a location. So you could think of this as like a map analogy. As far as how is it showing magnitude and direction, well, the electric field is everywhere tangent to the E field lines, and the density of the field lines is proportional to the magnitude of the field. So density of field lines in a given region of space is proportional, grows with, or gets higher with the magnitude of the electric field. So if I have a region where there's a lot of field lines, that will have a relatively strong magnitude, whereas a region in which there are relatively few or no field lines will have a weak magnitude. Now, again, this is an analogy only. When you're drawing field lines, you only draw a finite number of field lines, and so you will have regions where you just happen to have not drawn a field line, where the field is nevertheless quite strong. And that's just a function of, if I'm drawing a bunch of lines on a piece of paper like this, let's say, there are more space between these lines than there are covered in the lines. But I can make some generalizations, such as that I have a high density in this region right here. So this is high density, and therefore would represent a strong field. And then somewhere down here, here's a loop of equal size, actually maybe a little bigger. This would be low density. There's not very many lines per space. There's no line, say, right here. I'll make a little mark in, let's say, green for contrast. Whoops, I didn't select the green though. So there's no line at all drawn here, but nevertheless, the field is still high. so the field magnitude is still large, or you could say the field is still strong at this location. And again, this is just a function of the fact that I can't draw infinitely many lines. You're just drawing a sampling of lines. Okay, so that is basically, in a nutshell, what the field lines do. How do we draw them? Well, we need a set of rules for this. So rules for drawing field lines. And this set of rules, if you follow them correctly, then you'll have a reasonably good representation of what the electric field looks like in a given region of space. Rule number one is that all lines will originate on a positive charge. Okay, so that means if you do have a positive charge, then a line or set of lines can originate on it. If you do not have a positive charge, then you don't have an origin point for your field lines, and so if there are field lines present, then they have to originate from infinitely far away. The corollary to this, by the way, is that all positive charges or represented positive charges are origins of field lines. Okay, and the second rule is sort of the converse, which is that all lines terminate or end on negative charges, and same corollary about all negative charges being termination points applies here. So same corollary as above. What do these two statements look like? Let's say that I happen to have a positive charge somewhere. Maybe I have a little plus charge right here. Well, the field lines have to originate on it, and so they will start on this charge and just kind of move off. And they tend to, local to the charge, radiate from a given charge, but there's a little more to it than just that. So this would be a fine local drawing for a plus charge. If I wanted to have a minus charge, my field lines would basically look like this. Instead of radiating out, they kind of radiate inward. So the arrows point towards the charge instead of away from the charge. So that right there would represent a negatively charged particle. Okay. Next rule, rule number 3, number of lines originating on a charge has to be linearly proportional to the amount of charge, or directly proportional. So the more charge I have, and this is true for terminating as well, so we'll put that parenthetically, terminating for a negative charge, originating for a positive charge. This number is linearly proportional or directly proportional to the magnitude of the charge. So what that means is if these two both represent, let's say like 1 millicoulomb or something, then if I wanted to draw for 2 coulombs, I would have a slightly different drawing, which would maybe look like this. So I'll draw a little line here. This represents, again, say like +1 millicoulomb. Then over here, if I wanted to do plus, and this is +2 millicoulomb, so twice as much charge, then my field lines have to be twice as numerous. And again, for individual point charges, you kind of want them to spread evenly about the charge. So instead of 4 lines as I drew for the first one, I now have 8 lines drawn for the second one. This is kind of an aside, then arrange lines evenly. Okay. Now, all 3 of the drawings that I've made here would represent essentially field lines for individual isolated charges. So the fact that they're individual isolated charges means that there's no interaction between them at the moment. Where it gets interesting is what happens when you have interacting charges. So multiple sources, there's an additional rule. In addition to all those other rules, we have rule 4. Lines cannot cross, but they can bend. Okay, so they can't cross, but they can bend. So let's come back to this idea of plus charge and minus charge, and let's draw what would happen if I have both a plus charge and a minus charge in some region of space. So I'll put a plus charge here, I'll put a minus charge here. Let's say that they both happen to have the same, so this one would be like plus Q, this one would be like minus Q. So they've got the same amount of charge for both of them. What does that look like? Well, if I draw a line running from here straight across to here, that line's valid. It starts on plus, it ends on minus. Now suppose I go about drawing additional lines. Maybe I draw 8 lines for each one. So this one right here, the next line would be coming off like this. The next line would basically be coming up like this. I've got a line over here like this. Got a line over here like this. Got a line coming down like this. One here, one here. Okay, that's 8. Now for this one right here, I'd have to have, a line coming in like this. One coming in basically like this. One in like this. One in like this, one like this. Let's draw this line continuing a bit more. One would come like this, and then one would come like this. So here's the problem. We have lines which are crossing each other. So I'm going to draw a big red no sign for this because we've got lines that are crossing each other here. These two are crossing and these two are crossing, so that's a no. So lines are crossing. So what does this thing actually look like? Well, again, I can start my line that should have been kind of going off like this here, and I can have a line that should terminate here. But instead of just continuing straight, this line essentially bends in such a way that it connects from the plus to the minus. And then similarly down here, I have a line that's going to bend so that it connects from the plus to the minus. Should be smooth like that. And all my other lines will tend to similarly bend. So I get something that looks like this, within the limits of my drawing ability, of course. So I'll circle this guy out in green, put a nice check mark. It obeys all the rules. Now, this field configuration that I've drawn here is a rough representation of the field due to an electric dipole. So a dipole consists of two charged particles of equal magnitude but opposite sign, which are separated by some distance in space. And it's a fairly common arrangement in physics, as we may see through the semester between reading your book and watching the videos. But it's not the only possible arrangement of charges, right? We could, for example, have a setup in which there are two charges with the same sign, okay? So two charges with the same sign might look like this. So I'm going to put a plus charge here. I'm going to put another plus charge here. And again, if I was just drawing the field lines for this, I'd have a line that radiates out from this. I'd have lines radiating out from these. I'd have three collisions at least between lines, and more if I extend the drawing. Like this line that's going this way is going to hit the straight up line and the diagonal line, and so on. So there's going to be lots of collisions between lines, crossings, if you will. So my lines have to bend. Now they can't bend in the same way, because instead of being able to bend from this one so it connects here, I have two origin points. So my field line from this, instead of bending towards, kind of bends away from the other charge. And this one does likewise. It kind of bends a bit away from the other charge. So I end up with something like this. And then down here, I should get essentially the same pattern. So there's a symmetry to it. Okay. Well, since these two have bent, then the next two set of lines will similarly have to bend. So this one that would have been maybe a straight up line or a diagonal off line maybe starts bending like this. This one starts bending like this. Okay, and then my next two lines bend like this, and like this. And then maybe I happen to have a few that are bending more or less towards this direction. Okay, and this one, I get a similar set. One's coming off like this, one's coming off like this, and one's maybe coming like this. This one comes out here, this one comes out here, and this one comes out, it's not a very good bend, like this. So here's two charges of equal magnitude and same sign. By the way, if these were both minus charges instead, then the arrows would all be pointing inward along the lines instead of outward away from them. What about something more complicated? Okay, something more complicated. What if I have a long line of charges like this? So this is a long, thin line of charges. And I probably should be consistent and draw it in orange. So long, thin line. And the long, thin line, let's say, just continues on up this way as well. Obviously, I don't want to draw it all the way up here because I'll run into my other diagram. We can make it positive or negative. I guess since I did these as positive, let's make it negative Q total. So what would that look like? Well, essentially, if it's negative Q total, that's like having minus charges just kind of embedded in this line at equal increments. We're kind of assuming that it's a equal or uniform charge density. So there's these minus charges embedded at equal increments in our drawing. And each of these minus charges would represent something like -1. And so each of these would get the same number of field lines associated. Now, I haven't specified how many field lines that is. For a long line of charge like this, the easiest is to specify 2 field lines per minus charge that we're representing. You could actually do 1, but let's do 2 because the 1 looks kind of funky. So 2, they would need to not cross. And in order to accommodate that, basically, this means that they're going to be parallel lines, as I've drawn here. Since my charges are oriented horizontally, these parallel lines are oriented, the long line is oriented vertically, so these parallel lines are all oriented horizontally. And so my diagram looks something like this, where these lines really do continue off far this way and this way, but I'm not going to draw them all the way over because I need to draw the top view. So this is looking at it from the side. From the top, basically I just have a whole bunch of these charges stacked on top of each other like this, and so we could call these like, oops, I drew this as a positive charge though. We have a whole bunch of these negative charges stacked on top of each other like this. So basically we put all these lines together, but from the top, instead of just simply being 2 lines like this, because I now have a bunch of charges, I can have a bunch of lines. And to accommodate that, I let the lines be somehow symmetric about my charge distribution. And so I end up with something that looks basically like this from the top. Okay, so side view, top view. Okay, and this is, I've drawn both of these to remind us that field lines fill space, they do it 3-dimensionally. And so these drawings that I have here, they're all 2-dimensional sketches, but you can rotate this view to look at them from another direction. And when you do so, the field lines may look a little different. Basically, for this pair of charges, I have field lines that are bulging out and into the page within this region. So any side view, like if I look at it from the top or from the front or back, it'll all look like this. But if I look at it from the left or right, I more or less get very little in the way of field lines. The field is very weak over here and over here. And then down here, same thing. If I look from the sides, I actually get a whole lot of field lines coming kind of towards me. But if I look at it from the top or bottom or front or back, it'll look like this drawing right here. And then I have drawn 2 views of this long line of charge, and it looks somewhat different in those 2. And at this point, between all the examples I've done plus the discussion, the video is well over 20 minutes. I try to keep these short, under 15 minutes usually, and generally under 20. So I've kind of gone over my personal limit. Therefore, I'm not going to draw any further, except for just one. And the reason why one more is because I haven't done any kind of asymmetric charge distribution. And I feel like that deserves to be done as well. So let's make this plus 2q, and let's make this one over here be minus 1q. Okay, so this one is twice as big magnitude as this one. That means that I have to have twice as many lines leaving from this one as I have entering into this one. Oops. My first line can kind of leave straight from this one, go straight into the negative charge. My second line, which maybe I would draw along this direction. Leaves from here, curves gradually, and then has to basically enter the top of my charge here. And again, I'm leaving here, curving gradually, and then, oops, that's not very good. I curved too much there. Curving gradually, and then smooth enter the exact bottom of this one. Okay, so there's 3 of them. I then have another which leaves from, let's say, the top of this, and then curve, 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 and kind of curves down here to enter, let's say, the side here. This one right here does basically the same. Whoops, except for I'm not curving it enough. It comes in here. Okay, and now I've drawn 5. I need 5 more out of this one. So 1, 2, 3, 4, and 5. And these ones right here, which are curving here, they kind of have to eventually reconnect down here somehow. And typically what ends up happening is, if you're in this region right here, you have a very weak field because you have twice as much charge from this one as you do from this one. And the result is, and I'm actually going to redraw these 2 lines as well to make this point a little better. The result is that you end up with what we would call like basically charge shielding, which is essentially that you have a small amount of one type of charge that's closer to you. So the over R squared favors the negative, but the magnitude of charge favors the positive. And so they can actually cancel out. There is a region over here. Essentially, the ratio of the distances should be that this one is root 2 times as much far away as this one is. And so, that'd be somewhere over here where the field actually hits 0. And so there's not a whole lot of lines that are drawn in here. If we were to zoom way out, so zoom way out, that would put these 2, so I'll label it as +2 and -1. Then again, you have like this really, really strong field in this region. Like so. And then these lines, which were originally radiating outward, eventually end up kind of curving. Oops, that one's not a very good curve though. Kind of curving like so, and like so. And so from very, very far away, eventually what you get is the field that looks as if it's generated more or less by a single point charge. But the location of that single point charge ends up being offset slightly from the location of the actual positive charge. So if I trace back along these field lines once they sort of straighten out, looking basically like the field lines that would have been obtained for a single point charge located slightly offset. So like this one right here would essentially sort of like straighten out in such a way that if I were to trace back along it, it would end up kind of centered somewhere over here, kind of like at the center of charge point for this system. And I'm actually having trouble drawing this line for some reason. It's just cheating. I can't draw it there. Doing the best I can with this little drawing pad here. But that's your asymmetric charge distribution. And so if you're very, very far from the pair of charges, they effectively look like a single +1 charge with the 5 lines or whatever that we associate with that in this particular drawing. And so essentially, like what I've got here, these black dash lines are what you would see if you just had a set of lines just radiating out from this little black X here. Now, I've drawn more of them probably than what is warranted, for the simple reason that I was drawing as if there'd be like 8 radiating, and there's not, there's only 5. But this right here ends up looking like a similar pattern to just simply having a single +1 that we've drawn the field lines for. So essentially you end up with a set of field lines just running from far away with something else happening closer in. Ergo, why I have not drawn the field lines coming all the way in. But essentially, like, you could just say, oh yeah, they look like from far away they started here, but in actuality they're lines that have curved to get to this point. So that's it. That's all that I'm going to say about electric field lines in this video. It's much longer than my usual short videos, but I hope that you find it worth it. And thanks for watching. Rules.